Today, we'll be solving LeetCode 72, edit distance. This problem asks, given two words, what is the minimum number of single-character operations needed to turn the first word into the second? The allowed operations are insert a character, delete a character, or replace a character. Each operation counts as one step. This is a classic dynamic programming problem because we are optimizing a count across overlapping subproblems. The core pattern is bottom-up dynamic programming on substrings, where our state represents how many edits are needed to convert the first I characters of word 1 into the first j characters of word 2. First, let's define our state clearly so the rest of the solution flows naturally. We will build a two-dimensional table named dp. Think of dp at row I and column j as the minimum edits to convert the prefix of word 1 of length I into the prefix of word 2 of length j. That means dp at 0 and j is the cost to convert an empty string into the first j characters of word 2, which is just j insertions. Similarly, dp at I and 0 is the cost to convert the first I characters of word 1 into an empty string, which is I deletions. These two facts give us the base row and base column. Next, let's talk about the transition, which is the engine of the algorithm. If the ith character of word 1 and the jth character of word 2 are the same, remember, if we index from 1, this means comparing the character just before position I in 0-based code, then we do not need any new operation to align these two characters, so dp at I and j simply copies dp at I-1 and j-1. Otherwise, the characters differ and we must choose one of three edits: insert, delete, or replace. If we insert a character to match word 2's jth character, then we have solved the subproblem dp at I and j-1 and add one operation for that insert. If we delete a character from word 1, we have solved dp at I-1 and j and add one operation for that delete. If we replace the current character, we have solved dp at I-1 and j-1 and add 1 for that replacement. We take the minimum of those three choices and add 1. Now, let's walk through the code line by line and explain why each line exists and what it does in plain, beginner-friendly terms. We begin by reading the two input strings and storing their lengths in two variables. Let's call them m for the length of word 1 and n for the length of word 2. Then we create the dynamic programming table with m+1 rows and n+1 columns, and we fill it with zeros to start. We do this because we are going to fill in answers for all prefix pairs from small to large. Next, we initialize the first column. For each I from 0 up to m, we set dp at I and 0 to I. This encodes the idea that converting a prefix of length I into an empty string takes I deletions. Then we initialize the first row. For each j from 0 up to n, we set dp at 0 and j to j. This encodes the idea that converting an empty string into a prefix of length j takes j insertions. Now we are ready for the nested loops that fill the table. We say for each I from 1 to m, and inside that, for each j from 1 to n, we compute dp at I and j. Inside these loops, we first check whether the current characters match. We look at the character of word 1 at index I-1 and the character of word 2 at index j-1. If they are the same, we assign dp at I and j to be dp at I-1 and j-1, because we can carry forward the cost without adding anything. If they differ, we compute three candidate costs. One candidate is dp at I-1 and j+1 operation, representing a deletion from word 1. Another candidate is dp at I and j-1+1 operation, representing an insertion into word 1 to match word 2's character. The third candidate is dp at I-1 and j-1+1 operation, representing a replacement. We take the minimum of these three candidate values and store that in dp at I and j. After both loops finish, the bottom right cell, which is dp at m and n, holds our final answer, the minimum number of edits to transform the entire word 1 into the entire word 2. We return that value. Why does this work? Because each dp cell depends only on previously computed cells that represent smaller prefixes, the table can be filled from top left to bottom right safely. We never use information that has not been computed yet. This is exactly the dynamic programming pattern: define a state, set base cases, write a correct recurrence, and fill in an order that respects dependencies. Let's also discuss complexity and a helpful optimization. The time complexity is O of m times n, because we compute one constant time transition for each pair of prefix lengths. The space complexity of the straightforward table is O of m times n as well, since we store a value for every cell. If memory is tight, we can reduce the space to O of n by noticing that to compute row I we only need row I-1 in the current row as we build it. That optimization uses a rolling one-dimensional array and carefully tracks the diagonal value, the previous row's previous column, to simulate dp at I-1 and j-1. For teaching clarity, we keep the full table in code. In practice, when n is large, consider the rolling array approach. To summarize the algorithm in plain words, we build a grid where rows represent how much of word 1 we have used and columns represent how much of word 2 we have used. We fill the first row and first column with simple counts of insertions and deletions. Then, for every pair of positions, if the characters match we copy the diagonal, if they do not, we take 1 plus the minimum of inserting, deleting, or replacing. The last cell is our answer. And that's how you solve LeetCode 72. Thank you for watching and let's keep learning.